You are looking at a carbon steel industrial fan rotor. A microscopic layer of dust coats the leading edge. In India, the cement sector produces 380 million tons annually through a continuous, energy-intensive process dictated entirely by the rotary kiln. This orthographic projection of a cement plant isolates the rotary kiln. It highlights the exact position of the induced draft, or ID, fan. This machine operates as the critical respiratory organ of the entire thermodynamic cycle. The physical burden placed on this hardware is immense. It must constantly pull high-temperature combustion gases and highly abrasive raw meal particulates through the system. Here, we see the accumulation of clinker dust on the fan blade, mapped as a topographical grid. When this massive centrifugal fan chokes on this exact dust accumulation, the entire manufacturing process collapses. An unplanned stop costs between 8 and 14 lakh rupees in immediate production loss. It forces maintenance crews into extreme temperature zones to execute dangerous emergency repairs. The standard protocol for monitoring these fans relies on vibration sensors. Operators accept this and wait for an alarm. The actual physics of failure follow a specific sequence. Dust accumulation creates an aerodynamic imbalance first. The heavy steel shakes long after that initial imbalance occurs. This visual comparison shows two distinct signals. On the left is a wide mechanical vibration wave. On the right is a dense, high-frequency acoustic wave mapped as a topographical grid. The wide vibration wave measures physical shaking. It requires massive force to register a reading, making it a lagging indicator of equipment health. By the time a sensor triggers a vibration alarm, structural damage to the trunnion bearings has already occurred. If the heavy machinery is shaking, the operation is already paying for the damage. Reactive maintenance forces facilities into an endless cycle of costly physical repairs. The solution requires a strict methodological shift. Operators must capture the leading indicators of aerodynamic drag and acoustic friction instead of measuring mechanical shaking. We achieve this by deploying physical hardware directly to the machine. Acoustic sensors and high-resolution current monitors attach directly to the ID fan casing. A localized edge AI model sits inside that aluminum enclosure. It computes the exact mass of the dust load in real time. Reading these specific friction metrics establishes a concrete predictive advantage. The model accurately forecasts a mechanical trip up to 72 hours in advance. A 72-hour window buys the operator time. Sudden operational panic is replaced with scheduled, safe intervention. This split-screen visualization tracks two distinct asset health profiles. The left side maps energy consumption curves tied to aerodynamic drag. The right side maps mechanical wear patterns, indicating bearing degradation. Increased aerodynamic drag silently spikes energy consumption, taking root long before mechanical bearings degrade. AI vision cameras provide a secondary, structural layer to the predictive model. Here, a geometric grid overlays the steel blade. These vision systems track exact physical degradation. They identify structural fatigue and microfissures that acoustic sensors might miss. Fusing acoustics, current monitoring, and visual data maps the exact physical state of the hardware. This creates total aerodynamic legibility. Predictive data provides zero value without a structured execution layer to act upon it. Physical chaos must be translated into organized, executable data. This logic map traces real-time sensor analytics from the rotor bearing. Data moves through an edge compute node, routing directly into a mobile-first computerized maintenance management system, like AuxMate. Plants deploy this in phases, beginning with manual sensor readings and advancing to full hardware integration. The workflow software dictates the outcome. The CMMS is the bridge transforming digital intelligence back into physical maintenance action. Indian cement plants operate under strict regulatory requirements. They must maintain continuous emission monitoring systems and adhere to CPCB compliance. An integrated CMMS automatically schedules these regulatory tasks. It initiates dust suppression records and tracks specific equipment calibrations. This system completely replaces disconnected paper registers. Every action generates a time-stamped, technician-attributed digital log. Automating this paperwork converts a severe regulatory closure risk into a frictionless, inspection-ready background process. Shifting to a condition-based scheduling model yields highly specific outcomes over time. Cement plants document a 68% reduction in unplanned kiln stops. This entirely eliminates the massive emergency repair premium. These reliability metrics stem entirely from strict, legible system architecture. Plant reliability managers can execute a low-cost 48-hour roadmap to test this exact architecture. Step 1 requires identifying and isolating a single high-risk ID fan. Step 2 requires attaching one combined acoustic and vibration edge sensor to the casing. Step 3 requires routing the localized API directly into the CMMS to trigger automated alerts. This simple sequence validates the signal before scaling the hardware across the plant. Optimization efforts eventually leave the digital software layer and return to the maintenance crews on the factory floor. Genuine technology removes fear from the physical world. It exists to restore human safety. Accurately mapping the physics of industrial failure buys the operator time. It replaces sudden panic with scheduled intervention, ensuring workers stay out of dangerous emergency scenarios and go home safe.